Good morning. So today we'll see about the gear drives design and analysis of spur gear. So first of all, mechanical drives. So by means of friction, you can transmit the power from one shaft to another shaft using belt drives or rope drives. Whereas by engagement, if you want to transmit the power from one shaft to another shaft by means of engagement, you can use gear drives and chain drives. Engagement means there would be meshing of teeth. Okay. So to understand the gear drive, first of all, we are going to consider two friction wheels. Okay. So suppose first friction wheel A is mounted on shaft by means of keys, and second is mounted on shaft B by means of key. And both are pressed together by a force, there would be reaction force Rn. So if disc A will rotate in the clockwise direction, so obviously disk B will rotate in the anti-clockwise direction. But what is the cause to make them rotating? Like first A is rotating by means of power that can be taken from any motor, and B is rotating because of friction force in between these two, and that friction force is Rn multiplied by mu, that is mu into Rn. But what happens in this? If you are going to increase or keep on increasing the load on shaft B, there would be a point where there will be a slip between A and B. So at that point, what will happen? If the force because of that output torque will exceed the force mu Rn, there would be a slip. So just to mitigate this phenomena of slip, what we can do? So we can provide a number of projections on both of the wheels like this. Okay, in this figure you can see these are the projection on both of the wheels, friction wheels. So here the projections provided on the periphery of wheel A will fit into the corresponding recess on the periphery of the wheel B. A friction wheel with the tooth cut on its periphery is known as gear or tooth wheel. The usual connection to show the tooth wheel is by their pitch circles. So these circles in these friction wheels, you can see these circles are known as pitch circles. Okay. And this wheel is with the projection on its periphery. This wheel is known as gear, right? So now we can discuss about the advantage of gear wheel over the belt and rope drives. Okay. So gear wheel is defined as tooth wheel which transmit the power and motion from one shaft to another shaft by means of successive engagement of teeth. Obviously, it is a positive drive and velocity ratio remains constant. Second, it may be used to transmit large power, and it can be used for small center distances of shaft. High efficiency, reliable service, compact layout because it can be used for small center distance between two shafts. But disadvantage because the manufacturing of gears requires special tool and equipment. Therefore, it is costly in comparison to other drives. And second, error in the cutting in tooth may cause the vibration and noise during operation, and it requires suitable lubricant and reliable method of applying it for proper operation of gear drives. So there are some disadvantages, but it offers a number of advantages over the belt drives and rope drives. Okay, so now the classification of gears are based on criteria. So first is based on the position of axis of shaft. So if the axes of shaft are parallel, And coplanar, those shafts are connected by means of this type of gear. These gears are known as spur gear. Accordingly, there can be helical gear, worm gear, bevel gears. So for the intersecting shaft, non-intersecting and non-parallel shaft, you can use the spiral gears. Okay, so this is the theoretical part, you can go through it. Second, according to peripheral velocity of gears, there can be a low velocity gear, medium velocity gear, and high velocity gears. If the gears having velocity less than 3 meters, it is known as low velocity gears. If the velocity is between the 3 to 15 meter per second, it is known as medium velocity gears. And if the velocity is 15 meter per second, more than the 15 meter per second, it is known as high speed gears. Okay, and according to type of gear, they can be categorized as external gear and internal gears and rack and pinion. So this is the just theoretical part, you can go through it. So next is important terminology used in gear for spur gear. Okay, so in this figure you can see this is the pitch circle. As we see in the friction wheel, this is the pitch circle, and these are projections provided on the periphery of the circular friction wheel, and these projections are known as tooth. Okay, so in this tooth you can say this is the outermost circle which can be drawn on the outer surface of this gear. Okay, and this circle is known as addendum circle. And the second, there can be one uh, root circle or addendum circle. This is the this innermost. This circle is known as addendum circle. And there can be one base circle. Okay, so base circle, actually base circle is when you are providing or manufacturing these tooth on the friction wheel, you have to follow a particular profile. That profile can be a cycloidal profile and involute profile. So why we are using the involute or cycloidal profile, we are going to discuss. So from base circle, you are generating that profile. This is the involute profile of the gear. Okay, and this is the addendum circle. So we provide the fillet over here from root circle to this base circle. This is the fillet. This fillet is just provided to strengthen the tooth. Okay, so you can say within this area or this space, which is from the base circle to root circle, the gear profile is not following the involute profile. This is the fillet. Okay, and from addendum circle to base circle, this profile will follow the involute profile, right? And here you can say this is the clearance. This from pitch circle to addendum circle, this distance is known as addendum circle. From root circle to this pitch circle, this distance is known as addendum circle. This is the face width. This is the top plane, and this surface is known as the face, which is in between the addendum to pitch circle, and this surface is known as flank of the tooth. Okay, and this distance from this point to corresponding point on the adjacent teeth, this is known as circular pitch, right? This space is known as tooth space. Okay, so next is what is the pinion, which one is the gear. So smaller one out of two mating gears is known as pinion, and larger one out of two mating gears is known as gears. Then the velocity ratio. Velocity ratio is the ratio of angular velocity of the driving gear to the angular velocity of driven gear is known as speed ratio or velocity ratio. The next is transmission ratio. So transmission ratio in the case of gear trains, if we represent the angular velocity of the first driving gear to the angular velocity or angular speed of the last driven gear in the gear train, that ratio is known as transmission ratio. Then the pitch surface. The surface of the gear, the pitch surface of the gears are imaginary plane, cylinders, or cones that roll together without slipping. The pitch circle is the curve of the intersection of pitch surface of revolution and plane of rotation. It is an imaginary circle that rolls without slipping with the pitch circle of the mating gear. The pitch circles of pair of mating gears are tangent to each other, as we seen in friction wheel case. Pitch circle diameter. The diameter of pitch circle is known as pitch circle diameter, and during this lecture we will designate it by d prime. Then the pitch point. The pitch point is the point on the line of centers of two gears at which two pitch circles of mating gears are tangent to each other. So in this case, here you can say this point is the pitch point, right? These are the pitch circle, and at this point these two circles are tangent to each other. So this point is, and this is the line of center for both of the mating gears. So top land and bottom land, as we seen in the figure. Then the involute. The involute is a curve traced by a point on a line as the line rolls without slipping on a circle. Like, to understand this involute, you can assume that if you are having a cylinder and you are wrap a thread on it, now you just catch that thread from a point and unwrap this. So from that point you have catch that thread, that path traced by that point is the involute profile. Okay. And base circle, the base circle is an imaginary circle from which the involute curve of the tooth profile is generated. Okay, so now from the base circle to addendum circle there would be a involute profile of tooth, but from base circle to root circle, or you can say the addendum circle, there would be a fillet. So you can see in between that space the tooth will not follow the involute profile. This phenomena will help us to understand the interference in next slides. Then the addendum circle, already we have discussed. Then the addendum HA, this is the distance between the pitch and addendum circles. Addendum indicates the height of tooth above the pitch circle, right? Similarly, the addendum is the radial distance between the pitch and the addendum circle. The addendum indicates the depth of the tooth below the pitch circle, right? Then the clearance. The clearance is the amount by which the addendum of a given gear exceeds the addendum of its mating tooth. Then the fillet radius, the radius that connects the root circle to the profile of the tooth is called the fillet radius. And this is provided just to strengthen the tooth. Circular tooth thickness, the length of the arc on the pitch circle subtending a single gear tooth is called circular tooth thickness. Theoretically, circular tooth thickness is the half of circular pitch. Then the tooth space, working depth, hole depth, we can see these all from that figure. Now the center distance. The center distance is the distance between centers of pitch circle of mating gears. It is also the distance between centers of base circle of mating gears, right? Then the pressure angle. The pressure angle is the angle which the line of action makes with the common tangent to the pitch circle. The pressure angle is also called as the angle of obliquity. It is denoted by alpha. So this is the important terminology in this gear design. So from here we can understand like both of the mating tooth is uh, like you can say you can draw a common tangent at the point of contact, and you can draw a common normal at the point of contact, and the common normal is always tangent to the both of the base circles of the mating gears. So angle between the common normal at the point of contact and common tangent at the point of contact is known as pressure angle. Then the line of action is the common tangent to the base circles of the mating gears. The contact between the involute surface of mating tooth must be on this line to give a smooth operation. The force is transmitted from driving gear to driven gear on this line. So from this animation, we can understand the line of action. Now, you can see this is the base circle of one gear, and this is the base circle of another gear. And this red line is the common tangent to both of the base circles. Now you can see this, the point, at this point, both of the tooth comes into the contact, and this point of contact is continuously traveling on this line of action, and at this point, this red point is diminished at this point. So you can say at this point, the contact is end, and from this point the contact is started. So this red point is showing us the length of arc of path of contact, right? So you can say this is the common tangent, and you draw the addendum circle of this gear, so it will cut the common tangent at this point. The addendum of this gear will cut the tangent at this point. So in between these intersections of addendum circle of both of the gears, this is known as path of contact, right? And this point is always travel on the straight line, and this line is known as line of action. Now, similarly, you can see this phenomena here also. So you can say addendum of this gear, the upper one, will cut this line of action at this yellow point. This is the addendum circle, and addendum circle of this gear will intersect with the line of action at this yellow point. So you can say the contact will start from this point and end at this point. So this is the path of contact, and this line is known as line of action. So next is circular pitch. The circular pitch is distance measured along the pitch circle between two similar points on the adjacent teeth, and this is mathematically this is designated by pi d over z. Here d prime is pitch circle diameter and z designates the number of teeth. Then the diametral pitch. The diametral pitch is the ratio of number of teeth to the pitch circle diameter. This is z by d prime. So by using these two equations, 17.1 and 17.2, you can see P, small p represents circular pitch and capital P represents diametral pitch. If we multiply these two, so this will be equal to pi. Next, most important terminology, which is module. Module is defined as the inverse of diametral pitch. Therefore, M equals to 1 by capital P, or you can say D prime over Z. So D prime is module multiplied by number of teeth, or you can say circular pitch equals to module times of number of teeth. Now, the center to center distance between two gears can be given by the sum of radius of circular pitch circle, right? And in the diametral form, this can be written as dp. P stands for pinion, and d prime g stands for gear. Gear is known as larger one out of two, and p is the smaller one out of two. So this can be written as 1 by 2 dp prime plus dg prime. And in the form of module, you can write dp equals to m multiplied by zp. Zp is the number of teeth on pinion, and m zg is the number of teeth on gear. And now you can write m zp plus zg over 2. This is the center distance. A represents the center distance between the centers of two mating gears. So already we discussed about these things. Now, the law of gearing. Law of gearing is like the common normal to the tooth profile at the point of contact should always pass through a fixed point called the pitch point in order to obtain a constant velocity ratio. Right. So if we do some mathematics, or we use these triangles and apply some trigonometry relationships to get the velocity ratio omega over omega 1, we'll see the omega 1 over omega 2 will be O2P over O1P. O2P is the pitch circle diameter of gear 2, and O1P is the pitch circle diameter of gear 1. And omega 1 is the angular velocity of gear 1, and omega 2 is the angular velocity of gear 2. So omega 1 over omega 2 would be equal to O2P over O1P. So we can say, in order to have a constant angular velocity ratio for all the position of wheels, the point P must be a fixed point called pitch point for two wheels. In other words, you can write one statement: the common normal at the point of contact between the pairs of teeth must always pass through a pitch point. This is fundamental condition which must be satisfied while designing a profile for teeth of wheels. It is known as law of gearing. So this law of gearing, or you can say this condition, is fulfilled by teeth of involute form, provided that the root circles from which the profile are generated are tangential to the common normal. If the shape of tooth profile is arbitrarily chosen, so the another tooth is designed to satisfy the above condition, we have to design the another tooth which is going to match with one arbitrary profile chosen by us. Then the second tooth is said to be conjugate to first one. But this arbitrary tooth are not common in use because of difficulty in manufacturing and cost production. So like if you say D1 and D2 are the pitch circle diameters of wheel 1 and wheel 2, and T1 and T2 are the number of teeth on respective gears. Then the omega 1 over omega 2 is the pitch circle diameter of 2 over the pitch circle diameter of 1, or you can say inverse to the diameter of both of the gears. Similarly, you in the form of teeth you can write T2 over T1. So Now we can discuss the phenomena of interference in involute gears. So from this figure, you can say this is the actual addendum, or you can say addendum circle of the gear 2, and this is the addendum circle of gear 1. So the addendum circle, or this is the base circle of gear 1, and this is the base circle of gear 2. Now we will draw a common tangent to both of the base circle. This is this MN, or this is also known as the common normal at the point of contact, and this P point is known as pitch point. This is the pitch circle of gear 2, and this is the pitch circle of gear 1, and this is the center line. O1, O2 is the center line for both of the gears. So this is the pressure angle phi for pinion, this is the pressure angle phi for wheel. Okay, so you can say the addendum circle of this gear will intersect with this common normal or common tangent to the base circle at the point K, and the addendum of this pinion will intersect at the point L. So you can say this will be the path of contact, KL. Now if we keep on increasing the addendum of this wheel, the point K will keep on moving towards this point, and it will overlap, superimposed on the M. And if we keep on the increasing the addendum circle of this pinion, the L will keep on moving towards N. Okay, so now the contact will start from this point and end will end at N point. Now we can say if we further increase the addendum of this pinion or this wheel, this intersection point will move further from this M. And what happens, because from base circle to addendum there would be an involute profile of the tooth, but below the base circle, or you can say between the base circle and root circle, there would be a arc, right, fillet. So if we keep on increasing this addendum circle, so you can say the contact between, because this is after this pitch circle to addendum circle there would be involute profile, but after this base circle there would be a fillet. So you can say there would be interaction between the fillet and involute profile. So you can say both profile which are in contact are not same, so there would be a undercutting of the pinion. Or you can say the addendum or the tooth of this O2 will remove some material from O1 at the fillet, because there is interaction between involute and non-involute profile, and this material removing phenomena or undercutting phenomena is known as interference. So you can say the limiting condition reaches when the addendum circle of pinion and wheel pass through the points N and M. So you can say if we want to avoid the interference, we cannot increase the addendum of this O1 gear further from this maximum addendum circle, and O2 we cannot increase the addendum circle beyond this point, right? So this M and N imposing the limiting conditions for respective gears. So mathematically we can see, like you can assume that T is the number of teeth on the pinion and capital T is the number of teeth on the wheel. M is the module of both of the teeth. R is the pitch circle radius of the pinion. In the form of module, you can write mt by 2, and G is the gear ratio capital T by small t or capital R by small r, and phi is the pressure angle or angle of obliquity. So by from this triangle O1 and P, O1 and P, you can write O1 n square is equal to O1 P square plus P n square minus 2 O1 P Pn cos O1 Pn angle, O1 Pn angle. Okay, so this O1 P is the radius of pitch circle. You can write R square, and Pn is capital R sine phi, capital R, because this is capital R, this would be O2n is R, capital R cos phi, and this is Pn is capital R sine phi. So mathematically you can write small r square capital R square sine square phi minus 2r sine 2 small r capital R sine phi cos 90 plus phi. This angle is cos 90 plus phi. So by using or simplifying this equation, we'll get one formula, and that formula would be something like this. O1n, limiting radius of pinion addendum circle, small mt divided by 2, 1 plus t by t, and this term. So t by t is gear ratio as we defined here, G. So this O1n is the maximum addendum circle, or AP multiplied by module is addendum of the pinion, and AP is the fraction by which the standard addendum of one module for pinions would be multiplied by in order to avoid the interference. So addendum is the height of gear beyond the pitch circle, and that can be written as O1n minus O1p, O1n minus O1p. So this is the addendum. So this addendum can be O1n can be written in the form of module APM is equal to this formula. O1p is mt over 2 because O1p is pitch circle radius. Okay, so now this can be written as m will get cancelled out by this m, and AP will be equal to t by 2 and this term. So small t can be written as small t is the number of teeth on pinion. So we'll get this formula. Okay, so you can say in order to avoid the interference, the minimum number of teeth on the pinion can be obtained from this formula. Now the standard system of gear tooth. All standard system prescribed in the involute profile for gear tooth. The involute profile satisfies the fundamental law of gearing at any center distance. If we are going to change the center distance between both of the gears, still we can get the constant velocity ratio. All involute gears of a given module and pressure angle are completely interchangeable. All involute gears of a given module and pressure angle can be machined from one single tool. So you can go through this theory, and these are the standard tooth system. The first one is 14.5 degree full depth involute, and from here you can get the respective dimensions. 20 degree full depth involute system, 20 degree stub involute system. Okay, and if we are going to design the tooth, standard dimensions you can pick from these figures, and in the book there is a one table, from that you can pick the respective dimensions like this. If the pressure angle is 14.5 degree, the addendum is m, then the addendum you can get 1.157 m clearance, then working depth, hole depth, tooth thickness. We can obtained using these standard formulas. Then this is the recommended series of module. You can choose or you can choose the module as 1. Then next you can choose 1.25. So these are the preferred numbers to be taken as module of gears. Here, this is for 20-degree full depth system are written as HA is addendum M. The addendum is 1.25 times of M clearance, then working depth, then fillet radius. You can all the dimensions of all the terminology used in the gear can be obtained in the form of module only. So module is important in the case of designing of gear. So now we can go through one numerical, like there is one pair of spur gear consist of a 20 teeth pinion meshing with the 120 teeth gear. The module is 4. We need to calculate the center distance, the pitch circle diameters of pinion and gear, then the addendum and addendum of gears, the tooth thickness, the bottom clearance, and the gear ratio. So ZP is given as 20, ZG means number of teeth on gear is 120, module is 4. So as center distance is the sum of pitch circle radius of both of the gears, and that can be written as in the form of module can be written as mzp plus zg divided by 2. So from here we can get the center distance between both of the gears. The pitch circle diameters of pinion and gear. The pitch circle diameter of pinion and gear can be given as this, because from the definition of module you can say m equals to dp over zp. So dp is equal to module times zp, so you can get 80 mm. Similarly for the gears you can get 480 mm. Next, the addendum and the addendum for both of the gears. So addendum ha equals to 1 times of module. You can refer these tables. Okay, so accordingly you can decide for tooth thickness, addendum, addendum, bottom clearance, and gear ratio is ratio of number of teeth or gear to the pinion, which is 6. Now the gear trains are, if the gear trains consist of 2 or more gears transmitting power from driving shaft to driven shaft, or you can say in the transmission, if we use more than 2 gears, then this system is known as gear trains. Like this is the driver gear, then this is intermediate gear, and this is the driven gear. So ultimately what we are doing, we are inserting the power, or we are giving the power at this gear, and we are taking output at this last one. This is the driven. So we can use this intermediate gear. So this system is known as gear train. So this is the important part, force analysis, to design the spur gear or design any gear tooth. So like, just to understand this force analysis, we have to understand the free body diagram. Like, if the in this case, if the pinion is driver, so we can say driver will impose the force on driven, and that force, as we see in the previous slides, that force would be in the line of action, or you can say in the pressure line. So this is Pn, force is imposed by this driver pinion on this gear, which is driven part. So this would be in the line of action, and this line of action is the tangent to both of the base circles Okay, and this is the common tangent at the pitch point. So angle between the common normal or line of action and the common tangent is uh, pressure angle alpha. So this is the force exerted by this driver on the driven in this line. Okay, Pn, and this angle is alpha. So Pn can be resolved into two components. One is tangential component and one is radial component Pr. So you can say this Pt will participate in the power transmission. Okay, because this Pt multiplied by radius of this will be the torque on this shaft. This R multiplied by this P, and PR will create the reactions on the bearings of this shaft. Similarly, from the reaction action rule, or you can say Newton's third law, we can draw the direction of the force on the driver, because there would be a force Pn just opposite to this Pn. This is the Pn, this angle is alpha. So we can divide this angle, this Pn in two components. One is PR, one is PT, tangential force and radial force. This is the pitch point. Okay. So force analysis, there are some points. In gears, power is transmitted by means of force exerted by the tooth of the driving gear on the meshing tooth of the driven gears, right? The driver will exert the force on the tooth of the driven. In this figure, the tooth of driving pinion exerting the force Pn on the tooth of driving gears. So Pn is exerted by this driver on the tooth of this driven. So you can say this Pn will result into two components, Pt and Pr, and correspondingly there would be a two component of force on the driven, Pr and Pt. So there are some assumptions. As the point of contact moves, the magnitude of resultant force Pn changes. This effect is negligible in the above analysis. Secondly, it is assumed only one pair of teeth takes the entire load. At a point of time, only one pair will take all the loads. This is the assumption. At times, there are two pairs which are simultaneously in contact. If the contact ratio is more than one, so you can say the more than one pair is in contact at a point of time. So, but assumption is only one pair is taking entire load at a time. The analysis is valid under the static condition. That means when the gears are running at very low velocity. In practice, there is a dynamic force in addition to the force due to power transmission. So in the coming time, we are going to discuss the dynamic effect also while we are designing the spur gear. So in mathematics, like the power transmission can be written as 2 pi n multiplied by mt divided by 60 power in kilowatt. So mt can be written as 60 divided by 2 pi n. Mt is torque transmitted by gears and power transmitted by gears in kilowatt. So in to converting into watt, we can write 10 raised to power 6. N is the speed of rotation RPM. So the tangential force PT acts at the pitch circle radius. Therefore, the MT can be written as force multiplied by radial distance of the pitch point. So that is d prime by 2. D prime is pitch circle diameter. Okay. So from here you can write PT equals to 2MT over d prime, and PR and PT, like PT tangential force is the cos component of Pn and radial force is the sine component of Pn. So PR and, like here, Pn is equal to Pt over cos alpha and Pn is equal to PR of PR divided by sine alpha. So PR and Pt can be written as PR equals to Pt tan alpha. So This is the free body diagram for to decide the direction of PT and PR on both of the gears. So you can say one thing to remember, the driver will exert the force on driven. Okay, so from here you can decide the direction of PN. Okay, next PN can be resolved into two component, one is tangential and one is radial component. And similarly, you can decide the direction of PT and PN on the driven. This similarly, the reverse of, or you can say, according to Newton's third law, you can decide the direction of PT and PR on the driver. So these are the points already we have discussed. So in this force analysis, you can go through this numerical, right? So here are three gears. One is A, then one is P, and third one is C. And we know the power at 700 RPM through its shaft and rotates in clockwise direction at the shaft A. B is the idler gear, while C is the driven gear. The number of teeth on A, B, and C is respectively 30, 60, and 40, while the module is 5 mm. So we need to decide the torque on each gear shaft, the component of gear tooth forces, means PT and PR. So you can go through this numerical. This is very simple as we discussed. So here we will end this lecture. Thank you.